in order to understand the atmosphere and really make a forecast about it, we got to understand its composition, its structure before we can move on too far into this. So with that in mind, we're going to talk about the composition and structure today. So the atmosphere is impacted by different things, even dust. For example, dust from Africa, you can see it on the satellite here, can come all the way from Africa across into South America and even into the Caribbean Sea and even into southern United States. It occurred last spring and early summer where there was a lot of dust from Africa came across, and actually it reduced visibilities down to a quarter of a mile in some of the Caribbean islands just from dust. So what happens in one part of the world impacts another part of the world as far as the weather goes. It's all homogeneous. And these dust things can actually trigger algae blooms in the Gulf of Mexico. And they harbor some kind of disease causing organisms and actually cause people to get sick when they come across. So weather can go from tranquil to very violent very quickly. We've all seen it happen with thunderstorms and all. So let's take a look at how the atmosphere is composed. It's basically an Earth system that includes the atmosphere, the hydrosphere, which interact, which is just water, the geosphere, which is the planet, topography, and the biosphere, which is plants and us. Each one of those systems interact with the other. And the atmosphere is relatively thin. You think about it, half of the mass of the atmosphere is within 18,000 feet. So if you walked a little over 3 miles horizontally, you would reach half the way through the atmosphere if you could walk that vertically. So 99% of the atmosphere is within 20 miles of the Earth's surface. So if you ran a marathon, you've run through the atmosphere in the vertical. The atmosphere is pretty homogeneous in the lower layers. What that means is that roughly any point within those first 20 kilometers or 20 miles is 78% nitrogen and 20% oxygen. So above that, they begin to separate out some. But since we're worried about weather forecasting, we don't really get into above that too much. So you can see it here. One of the things, like, for example, a pilot might think about is if they're flying, the amount of oxygen, the percentage of oxygen is the same. It's just that the amount of air is less if they're flying at 38,000 feet versus when they're flying at 5,000 feet. So even though the percentage is the same, the amount, because the air is less, amount of air is available, is less. So the Earth's atmosphere also has aerosols. They come from ocean spray. You saw the Saharan air layer coming across there with dust. And they can come from industries. Factories can put them out. Water vapor is another component. It's basically less than 4% of the atmosphere in the lowest 1 kilometer. It's all pretty much down close to the ground. And it's necessary for clouds and precipitation. CO2, it's required for life. We got to have it for photosynthesis and plants growing. And CO2 and water vapor are two of the primary greenhouse gases. What that means is they actually absorb a form of radiation called infrared, and it keeps the lower atmosphere warmer than it would otherwise be. Otherwise, we have a very cold planet. And here you can see a lot of the dust, man-made or otherwise, like settling into smog in Los Angeles here. One of the parts of this study we talk about is a scientific method. Any course in science is going to have this. You look at observations and you ask questions. For example, if I looked at, we'll say, a thunderstorm that was moving across the Ohio River, and I wanted to know why that thunderstorm died out as it moved to the south side of the Ohio River, I might ask a question, pose a question about why, and then I'd form a hypothesis about that. Then I would test that hypothesis. I might look at other observations where that happened or didn't happen, and see if I can figure out and draw some conclusions from that. And eventually I get to the point where what I understand supports that hypothesis. And every time I'm seeing that thunderstorm either increase or decrease as it goes across the Ohio River, I can explain why. And that's like the scientific method for weather. And you do it in all different sciences. And in studying weather, we look at atmospheric models such as chambers that actually generate tornado vortices. We actually have numerical models which take in all kinds of equations. Everything you're going to learn in this course can be put into an equation of some form. However, very few of the equations can be solved. And we don't even know what's actually going on in the atmosphere right now for sure. We can see a little bit of it. You know the weather at your location, but I bet you can't tell me what the weather is 10 miles from that location exactly. And that little tiny difference can make a huge difference in what the forecast is. We have observation systems like ASOS. These are at every major airport. The reason they're there is that aircraft need to understand what the weather is right now for them to fly. If they don't know the weather, they're not going to be able to fly, either takeoff or landing. There are National Weather Service cooperative observing networks. They're unpaid, they're volunteers. They have instruments that look like this. Basically, the idea is they take records, daily records. Every morning at 7 a.m., they record a max temperature from the previous 24 hours and a min temperature. And they look at the amount of precipitation. All of that is tracked. The idea is to get hundreds of years worth of data of those observations. But it's not real-time ops for a meteorologist. We don't necessarily see that observation until the end of every month. There is community collaborative rail, hail, and snow networks. COCORAS, volunteer network, but it's a great way to get very quick observations of how much rain or snow fell or how bad the weather is. Radiosondes, we launch them every day, at least twice a day in about 100 locations across the United States and around the world. Other ones are lost. A radiosonde is basically a big balloon that expands as it's going up. It expands because the air gets less and less of the air around it. So the air inside the balloon just has to take up more and more space. As it expands, it eventually will break. But they carry these little radiosonde replacement system instruments, which basically record temperature, pressure, how much the wind is blowing, and humidity. Dropsonde is the opposite of a radiosonde. It has the same kind of instruments, but it's dropped out of an aircraft, so it sinks down into the surface. So it's going basically done over oceans, and it drops especially into hurricanes, sometimes into very strong extratropical cyclones that are off coast. The idea is to get a profile of temperature, pressure, dew point, and wind again. Remote sensing, such as radar or satellites, are used to collect observations and understand what's going on in the weather. Here's just a typical profile. Notice that as the atmosphere reaches tropopause, it begins to warm. And then it begins to warm more as it goes up in the stratosphere. So the troposphere always cools. So if you go up a mountain, you're going to keep getting cooler. But if you were to get above the troposphere and into the stratosphere, you actually could begin to warm up as you went up. We talk about auroras in this course very little, but they're caused by the solar wind and impact it has. And depending on the amount of solar wind, the further out the aurora is going to get. So with that, here's today's weather. We have a big low pressure system developing now along the East Coast. Earlier in the week, I pointed out the other day, what's left of that low is right here over Lake Michigan. But the stronger low now is actually redeveloped and is pushing a lot of clouds and rain. So if you were to look at a profile of the atmosphere here, and this is Nashville, you can see the winds, and you can see the temperature being plotted in the vertical, and it cools with height all the way up to right about 350 millibars. At that point, it begins to warm, and that is the edge of this tropopause right there, and you move into the stratosphere above that. So if you're in an airplane flying up at about 40,000 feet, you're actually flying in the stratosphere across Nashville right now. If you were to look at Detroit, notice the winds were all out of the east, and you saw Nashville was out of the west. So you have a big upper low that you can actually see by just looking at these two soundings and determine that there's a huge upper low system, and that is what's triggering the surface low. If you wanted to look at what's happening in the satellite realm, we can actually see the low rotating here in the clouds at all different levels. And here you can actually see very high clouds, bumpy little high clouds in here coming in off the Atlantic, off the Gulf Stream into New England. And that's generating precip, which we can pick up by the radar over that area. So you combine the radar intensities with the clouds, and you get a pretty good idea of where precipitation and what's going on. So this gives you just a picture of how we look at the atmosphere and begin to observe it, what the structure is, and what its composition. So let me know if you have any questions this week.